to introduce Professor Patrick Lee from MIT, but before I introduce him, I'd like to say a few words about the school. These public lectures are part of the Boulder Condensed Matter School. It's been going on, I think this is the 11th school. It's held every July. It goes on for 4 weeks. There's between 60 to 65, I think this year even more, of the top students and postdocs from around the world come to study at this school. It's supported by University of Colorado and by the NSF, so this is your tax dollars helping support American science and technology. So the subject of the school this year is computational and conceptual methods in quantum many-body physics. This field of quantum many-body physics underlies, I think, almost all of the modern science and technology today, but it's also a source of many very difficult problems, and that's why a couple weeks ago, our previous lecture was on computational approaches by Stephen White, an expert in that area. And this lecture is going to be by Professor Patrick Lee of MIT, talking about conceptual approaches to the problem. Professor Lee has been working, in fact, on many of the most difficult problems within this difficult area. In particular, he's known for his work on systems with strong interaction between electrons and systems with disorder. Two of the most difficult problems. He's received numerous prizes for this, including the Buckley Prize of the American Physical Society and the Dirac Medal. And on one final note before I let him start, I remember I took, years ago when I was a graduate student, I took the condensed matter physics course from Patrick Lee that he was teaching, and I found that he was not just an outstanding scientist, but he's an outstanding lecturer and explainer of ideas. So I hope this lecture will help you understand some of what's going on at the school this month.
Thank you very much, Matt, for a nice introduction. It's a pleasure for me to be here talking about some of the exciting things that have been going on in our field, and some of these are being discussed in the school these past few weeks. Let me first give an outline of what I want to talk about. I want to take this opportunity to explain a little bit what our field is about. Our field is called condensed matter physics, which is very unfortunate because it's a name that I think nobody knows what it means. You might have this experience. I go to a cocktail party and talk to people, and someone asks you, "What business are you in?" And say, "I'm in condensed matter." And you get this hustle look. And you know that what's going on in their mind is that they're thinking, "Oh, condensed matter. That must be a euphemism for compactified garbage." Maybe I'm talking to a trash compactor salesman. So I stopped telling people I'm in this business. So that's what I would like to correct some of this impression that people might have about our field. And I want to tell you about superconductors. It's a very fascinating subject, surprising properties. And I divided my talk into two pieces. There are conventional superconductors and conventional magnets. So those are the two themes of properties I want to explain to you. And I think the one way of describing what interests us is we are always looking for emergence of new properties at low energy scale or low temperature. Right? So the emergence means that these are things, properties that don't exist, or you would not have dreamt of existing, but somehow they showed up. And so that's very fascinating. And so this actually has become a theme in modern condensed matter physics today. And then I want to talk about unconventional superconductors, particularly high-temperature superconductors, which was discovered almost 25 years ago now. And they are unconventional because they live next to an insulator, which we'll call a Mott insulator. I'll explain what these words mean. And finally, a very current topic is the search for an unconventional kind of anti-formation, which is called quantum spin liquid. So I want to tell you a bit about that. And actually, I brought with you some demo which cover all four of these materials, as you will see. So let's start with, okay, so what is condensed matter? they decided that solid-state physics is not a good name. It's too restrictive, it's too specialized. They want to be more inclusive. So they invented this name, condensed matter physics. Right? So we are supposed to be called condensed matter physics. So that created this problem that nobody knows what we're doing. And solid-state physics people can respond to. We're the people that gave the world semiconductors, and transistors, and lasers. But what is condensed matter physics? So I think that's a huge strategic error. But it is an exciting field, as I will try to show you, and it's very special because it really lies in the intersection of three different disciplines. I think this is quite unique in the world of physics. First and foremost, there is a materials preparation because we study new material. So somebody has to come up with the material in the first place. So there are people who specialize in either discovering or creating new material or making very good samples of existing known material that experimenters can study and measure in the laboratory. And then there's a bunch of theorists lurking around who either try to explain what the experimenters see, or if they're lucky, they can predict what the experimenters would see, and with small chance of success. When this, ideally there should be resonance between these three groups of people, and when that happens, it's really a beautiful thing to witness and to live through. So I was fortunate enough to have been involved in a number of problems where such kind of an interaction really exists, and it's create a very exciting time. And so in this context, magnetism and superconductivity are really two of the most common novel properties that we encounter. And interestingly, both of these rely deeply on quantum mechanics to explain. You may think that a magnet is something that I found in my refrigerator door. It's something very commonplace. And usually you think of quantum mechanics as something kind of esoteric, and maybe only at very low temperature. You have to go to Gila to get this Bose-Einstein condensate before you see effects of quantum mechanics. But that's not true. I think a lot of phenomena we encounter would not be there without quantum mechanics. And magnetism is one, and in a very interesting way. So let me explain magnetism. So the ferromagnet, of course, has been known for thousands of years. Okay, and I have this is my first demo. I happen to have a replica of the first compass. This is a miniature replica of something made in the Han Dynasty. That would be around 2,000 years ago. And so it consists of a spoon, right? And on a copper plate. And of course the handle of the spoon would point south. So this phenomenon has been known for 2,000 years, but it was explained really only in the 1930s. And it has to wait 2,000 years because it has to wait for quantum mechanics to be invented. So what are the ingredients? So the quantum mechanics that we need to know are just two pieces of information I need to convey to you. One is that electrons carry, we think of electrons as point-like objects, very small objects, but in fact, there's an internal structure. They carry an angular momentum. They're spinning around. So we assign a spin to the electron. So the electron can either spin clockwise or anti-clockwise. We call it spin up or spin down. So that's the one ingredient. The second ingredient is that the world particles are divided into three classes. They're either fermions or bosons. And electrons turns out to be fermions, and they obey so-called Pauli exclusion principle. All that means is that two electrons with the same spin cannot occupy the same place. They're mutually exclusive. They can never sit on the same point. Now, particles, electrons with opposite spin, are able to interpenetrate each other, get as close as they can to each other. The same spin cannot. So those are the key ingredients of quantum mechanics. The third ingredient is more classical. We know that electrons repel each other, right? We knew that from rubbing cat's tail on something. and create charges. And Coulomb repulsion, that's known much longer, right, in the 19th century or before. So Coulomb repulsion is known. But electrons really don't like each other because of this strong Coulomb interaction. In fact, the main theme of my talk is that electrons really hate each other. They have a deep hatred for each other. And that's the source of all the interesting phenomena. Okay. So with these three ingredients, then we have a theory of ferromagnetism. Why? Well, first, in a metal, we have electrons that are running around freely. That's why they can conduct electricity. And there are two ways we can have these electrons running around in a solid. One is that we can have equal population of up and down spin. So the up spin is red and the down spin is blue. Right? So these electrons will be more or less randomly running around. So if you take a snapshot, they will kind of look like this. They will be randomly distributed. Okay? However, if you arrange for all the electrons to have the same spin, then they're all red electrons. And if you take a snapshot, they will look like this. Now, what's the difference between this snapshot and this snapshot? Well, in this snapshot, there are no electrons that are close to each other, right, because of Pauli's principle. Pauli says that this guy cannot be near here because there's a rigid quantum mechanical principle that says you cannot come next to me, right? You know, like humans, every human has a kind of a sphere of around it that he feels uncomfortable, right, when other people get through it. The size of the sphere depends on your nationality. Mine is quite large. so these electrons are, you know, they don't like each other. And so they guarantee, Pauli principle, guarantee that they stay apart. Okay? But whereas here, you see, this blue electron and the red electron, they don't care, right? They can wander close to each other and, you know, maybe stop to have a conversation or something. So that's a different picture. But now look, this guy is much worse from the point of view of Coulomb repulsion. And this guy costs me much more energy because these electrons are getting close to each other and becomes very costly. Right? So I can lower my energy by going to this state. Okay? And this is the origin of ferromagnetism. Right? The system decided they can lower its energy by having all the spins aligned. Right? When all the spins align, because the spin carry angular momentum, the entire sample is carrying angular momentum, and that creates a magnetization, which gives you a ferromagnet. Okay? So, you may ask, you know, why does this always happen? So, in nature, what's interesting in physics is always a competition. It's always some fight between two forces. So the competition is between this Coulomb repulsion, which the electrons wants to stay apart, and a kinetic energy, because the electrons want to run around freely. So if you do this, you pay a price in kinetic energy and you gain in this Coulomb energy. So that the mutual balance occasionally creates a state which favors this single spin. Okay. And in fact, ferromagnets are quite rare. And among the elements, the common elements, there are only iron, nickel, and cobalt, and a few rare earth elements that are ferromagnets. Okay, so this is actually this phenomenon is very familiar to us, but it's actually a rare bird. It's very hard to achieve this. Okay, now my next topic is superconductivity. And this was discovered by Kamanonis. This is his picture. In 1911, when he cooled mercury to liquid, well, actually his assistant did, cooled mercury to liquid helium temperature, and its resistivity just vanishes. Right? So that's very strange. So that's one way of characterizing a superconductor. You know, any metal has electrical resistance, but a superconductor has really zero resistance. It can carry current without any voltage. So that's a fantastic piece of property that must be very useful. Now, for 80 years, for 75 years, the highest transition temperature, so this happens only at low temperature. See, the reason he could do this was that he was the only guy, the first man in the world that was able to liquefy helium. So he had a monopoly on what we call low temperature physics for a number of years. And for some reason he decided to look at mercury. But until recently, the highest temperature, so this always happens at quite a low temperature, And the highest temperature you can achieve this is 23 Kelvin. Just to calibrate room temperature, in this Kelvin scale, room temperature is 300 degrees. And the lowest you can get is 0 Kelvin. Right? So this is like less than 10% of the way, right, to room temperature. So it's very, very cold. Yeah, so, but even though the temperature is very cold, superconductor is actually very commonplace. If you look at the periodic table, here we have colored all the, yellow is the color of all the elements, which actually become superconducting. Okay? And the highest transition temperature is, I think, niobium, which is superconducting at 9.5 Kelvin. The green are the elements which are superconducting under pressure or in thin film form, so they're more esoteric. But you can see that the blue and green covers pretty much 80% of the periodic table. Now the poor ferromagnet, there are only 3 of them sitting here. Now there's some exceptions. Of course, some of iron, if you apply very, very high pressure, it turns out to become a superconductor as well, but then it loses its magnetism. It becomes a different thing. So superconductors are actually commonplace, much more commonplace than ferromagnet, and but unfortunately they're limited to very low temperature. Okay, so how do you understand superconductors? Again, it took 50 years before people figured out the theory, and this was done by Vadim, Cooper, and Schreiber. So people thought, well, this was a long time. But of course, again, we have to wait for quantum mechanics to be invented before you have a chance of coming up with an explanation of something like this. So let me explain this theory to you, because it's actually quite simple. It takes 2 steps. Okay? The first step is to say that the electrons actually come together to form a pair, which we call Cooper pairs. So we imagine having a molecule of 2 electrons. So this would be a Cooper pair. Now, how do these electrons why would they come together to form this Cooper pair? Well, we can make this analogy of 2 bodies on a mattress. Okay. You know, being a physicist, the only body that I can imagine are spheres. So we have 2 spheres, and you put the first sphere on the mattress, that will deform the mattress, right? Think of this as a rather heavy body. So deform the mattress, and then of course the second body would basically roll in to this dimple that's caused by the first body. Right? So this is what's happening in a mattress. The same thing happens in a solid, because a solid has a crystalline lattice that is made up of atoms. The atoms can be formed in the presence of an electron. We call this lattice vibration. So an electron actually sets up some lattice vibration, much like when you jump on a mattress and start vibrating. And then the second electron will want to come and enjoy that vibration. So that's the explanation of why you want to make Cooper pairs. But now you should be very unhappy. You should object. Right? Why aren't you objecting? This picture cannot be right. Right? Why is it wrong? Well, because you already forgot what I told you. Electrons hate each other. Right? You've already forgot the main theme of my talk. Okay? So how can it be that these 2 bodies that hate each other wants to share a mattress? That is not possible. So, but nature is very clever, much more clever than humans. So what happens is that this attraction is short-range in space. They share the same mattress, but retarded in time. So what happens is that first the electrons are actually, what's wrong with the picture before is that I have sort of static bodies. But in fact, these bodies are running around very fast. The electrons are very light, and they run around very quickly. And the first electron with downspin is running quickly, but he leaves behind, it leaves behind a lattice vibration. The lattice vibration is very slow, right? And so the lattice vibration is still there, and then the second electron comes by with a downspin. Okay? And now because this vibration is slow, it can still enjoy the attraction of this vibration without ever getting close to the first one, because they're retarded in time. Okay? So this is how nature managed to solve this problem. Yeah. By the way, this solution was not discussed in the original BCS theory. They just assumed that they attract. Okay. Well, that's a nice story, but the only trouble is that the attraction strength is very weak. Right? Because we have to go through this retardation and through the lattice vibration and so on. And basically, fundamentally, these are repulsive forces, so you try to tweak out a tiny bit of attraction to form this super pair. And that's why the superconductivity is limited to very low temperature. But because this argument is quite general, it actually generally would like to happen. And that's why it's such commonplace. Most metals, in fact, become superconductive when you get cold enough. Okay, so what is step number 2? The second step, so that's not enough. So first you form these molecules, this group of pairs, right? The second step is to say that a pair of these electrons becomes bosons. Okay, so I told you that one electron is a fermion, so two of them turns out behave like a boson. And what's special about boson is that they can undergo what is called boson-side condensation. Now, that's just a complicated word to say that now these pairs of electrons behave like waves, quantum mechanical waves, rather than particles. So that's something fancy quantum mechanical. In other words, the superconductor is described by what we call technically a macroscopic wave function. Which is a complex number with a phase. But for our purpose, we can just draw the following picture. In short, so if I have a superconductor ring, so imagine this is a piece of superconductor made into a ring. Then at each point along the superconductor, we should associate an angle, right? So at each point along the wire, there's an angle that characterizes the state of this ring. Okay, that's all we need to take away from this. So once this Cooper pair forms and condense, then you can characterize everything just by this one number on each position. Now, the resistance of a superconductor, as I said, is exactly 0. It's very important to realize it's exactly 0. It's not just very small. Even at a finite temperature, the resistance is 0, not just very small. Repeat that. So small that if you take this ring, and if you have a current running around in the ring, it's been demonstrated that the lifetime of that current can exceed the life of the universe. The current will just keep on running until there's nobody else to be around to look at it. I guess we will never test this. Totally. So when you have something like this, as accurate as this, then the only explanation usually has to do with topology. Okay? Because topology is a science of yes and no, whereas algebra or geometry is a science of shapes and continuity. So to explain this to you, I brought along my own. I usually travel with my own superconductor belt. So this is my second belt. So this is, I claim this is a superconductor, and it works at room temperature. So think of this as a wire. This is my superconducting wire, right? And I said that on every point along this wire, I assign a number, an angle, right? So I have this wire, so I can twist this belt, and so you see this thing would form an angle. Right? As I twist this, right, then this is that. So this is the angle that I want to assign. So this is the angle that I draw it. Okay, so this is an angle. Now, when I take a superconductor and twist this angle, it turns out that then a current will flow along this wire. You can't see this current, but it's there. Okay, so now to make this persistent current, I can do two things. Right? If I just close my belt like I usually would, then this doesn't carry any current, but thermal fluctuation would cause these things to wobble, right? But that doesn't change anything. Now, to carry current, I have to twist the belt one time and hook it back again. Right? So that is a topological transformation because I have made a knot, essentially. I twisted this belt. And no matter what I do, no matter how hard I shake this, I can never get rid of this twist. Okay? So this twist is always there. Okay? And with this twist, that means that there's always a current running around. And I have no way for me to get rid of this current. Okay, unless I break the belt. There are ways to do that, but we don't talk about breaking the belt. Right? So there are different states of this superconductor. You can twist it once or twice. You twist it the opposite way, and the current runs the opposite way. Okay, so that's how a superconductor works. Right? Clear? I will sell this to anyone who's interested in room temperatures. I should start a company. Okay, so I think this is explains all we need to know about superconductors. Okay, so let me continue my story about magnets. So there's something called anti-ferromagnet. So I told you the story of ferromagnet, which is what the Chinese already knew 2,500 years ago. Now, for anti-ferromagnet is a much more recent history, and it was first postulated theoretically around the 1930s by Louis Dayal. And as I will show you later, initially this theory was met with a lot of resistance. Nobody believed it, that there was such a state. And finally, I think in the 50s, my late colleague, Cliff Shaw, did a definitive experiment, the neutron scattering, that proved the existence of these anti-ferromagnet. So compared to ferromagnet, anti-ferromagnet has a much more recent history. Okay. And so now how does anti-ferromagnet work? Why do things want to form anti-ferromagnet? Again, it has to do with these electrons that carry this spin. But this time, usually these electrons are not mobile, they form an insulator. Okay? And so why is that? Well, again, this has to do with the hatred of electrons to each other. Because I have one electron it's like a musical chair. And I have these chairs that these electrons can sit on. And so usually the electrons want to run around to gain kinetic energy. But if the mutual repulsion is strong, then it costs me a lot for these electrons to live here, because then they have to share the same site. And they have to pay a big Coulomb repulsion. So if that Coulomb repulsion is big enough, the electrons will just give up running around and just say, no, I just stay at home. So everybody just sits at home, and then it becomes an insulator. Okay. Now it turns out that insulator is called a Mott insulator for technical reasons. And it turns out that it's better for these electrons to have the spins aligned oppositely from each other. And again, it has to do with quantum mechanics, because if the spins are parallel, then Mr. Pauli says that there's absolutely no way for them to meander. So, this guy, even though they hate each other, occasionally they may want to, go out and buy some milk or something. So he would go try to go next door. But if the next door guy has the same spin, he's absolutely forbidden to go there. But if it's opposite spin, then they can sneak out and come back. Okay? And that's why this is a better state. And so this is the reason for anti-ferromagnet. So again, quantum mechanics and repulsion. Right? So those are the big themes I want to get in your head. And in fact, anti-ferromagnet, after they've been discovered, is quite common among transition metal oxides. And even among the elements, so now I can fill up the periodic table. Now with the purple, I have the anti-ferromagnet, and they're quite commonplace around the rare earth and chromium and manganese and so on. So now you can see that I've practically covered the entire periodic table. Right. So except for the inert gases, by the name they're inert, they don't do anything, or the simple metals, copper or potassium. All these systems, they become unstable. They find some state they get into at low enough temperature. So that's part of what we call emergent property. Right? Things that are happily a metal or an insulator becomes these weird objects at low enough temperature. Okay. Now, one thing you notice in this table is that superconductors and magnets are mutually exclusive. So I have all this yellow and blue and this color code. They don't overlap. With a few exceptions. When that exception happens, it's usually under high pressure, and the element goes into a different phase. Okay. So we need an explanation. Why are superconductors and magnets mutually exclusive? Okay. Well, the ferromagnet is easy because the Cooper pair, as I explained to you, is formed by opposite spin. Okay, the opposite spin, but the ferromagnet wants spins to be parallel. So that's immediately a conflict. Right? So in the ferromagnet, I cannot form opposite spin. So this explains why superconductor cannot coexist with ferromagnet. Now, why can't they exist with antiferromagnet? Well, in fact, most antiferromagnet are insulators. I explained to you that because of the strong repulsion, the electrons are staying still. They're not running around. But for someone to be a superconductor, first it has to be metal because it has to conduct electricity with no resistance. So that is orthogonal and opposite to being an insulator. So that's why we have this mutually exclusive world. So the story changed 25 years ago with the discovery by these gentlemen, Bedfellows and Mueller, of a new class of material called the high temperature superconductors. And the transition temperature, the highest achieved is about 150 Kelvin under pressure. So that bring them superconductivity to halfway to room temperature. Right? Room temperature is 300 Kelvin. So that's a very exciting development. And the big barrier is liquid nitrogen temperature of 77 Kelvin because liquid nitrogen is very readily available, and in fact I think costs less than the bottled water. So that's a real breakthrough, and they were immediately recognized with the Nobel Prize just 1 year after the discovery. So here's a plot of the history of superconductors. Starting from 1911, mercury is down there. And you can see that gradually with time, slowly, the transition temperature increases. But in 1987, suddenly it jumped by a factor of 5 to these very high temperatures. So now it's clear that this is a game-changing event, right? That these characters must be very different from these guys. And interestingly, after the discovery of these high temperatures, conventional superconductors continue to rise with a lowly pace in their transition temperature. And the most recent exciting development is that 2 years ago, people discovered a new class of superconductors based on iron, which is again a big surprise because iron we usually associate with magnets. Okay, so this is what happened. So we have to explain why. So clearly something very exciting has happened. But before I do that, let me just say one more thing about superconductors. A key feature of superconductor is that it repels magnetic field. The superconductor, so if you put a magnet above the superconductor, then the magnetic field of is repelled by the superconductor, and as a result, this magnet can be levitated in space. And many of you probably have seen this picture where we have a high temperature superconductor sitting in a bath of liquid nitrogen, and the magnet is hanging in space above it. Okay, as many of you know, physicists very often like to have big and useless plots. So here's an example. So if you start with something like this, and you say, oh, okay, let's, if you can levitate a little piece of magnet, let's levitate something bigger. So you can levitate a goldfish in this container. But why stop there? So you can levitate a person. If you notice there's a gap between this plate she's sitting on and the bottom of the piece. So if this is a ferromagnet, and this thing, is cooled with the liquid nitrogen and so on and so forth. So if you can do that, why stop there? So they managed to levitate a super wrestler weighing, 300 pounds. It's actually the weight of an average American. But again, if you look at it carefully, there's a gap between where he's standing, and they even amplify it, so in case you don't believe it. Okay? So these are useless objects, of course, but of course the goal is to eventually levitate a train so they can go 500 miles an hour and so forth. But I think those are quite far away in practice. But in fact, I think after 20 years of development, I think the applications of these high temperature superconductors may really be just around the corner. So in technology, it often takes a long time to develop the material. So particularly the case of superconductor, the materials are so difficult to handle. It takes people many, many years to learn how to manipulate them and get them into nice form. So for example, you would like to make wires. So this is an example of what they call second generation wires, which they can make kilometers long of these wires by this company, American Semiconductor. Probably the most successful company, actually, probably the only one that survived all these years. So I think there are niche applications that have already been in existence. You can find high temperature superconductors in cell phone substations, in their filters or their microwave filters. But the large-scale applications, for example, this is 2 years ago, they built the first transmission cable in Long Island. This is a 2,000 feet long system that carrying a current. Another application that's very interesting that people are talking about is to use them for in wind farms to make these wind turbines. So I didn't know this, but the question is, what is the limitation of how big you can build these turbines? Usually, the bigger the better. Right? The bigger you can build, the more efficient it is. But it turns out the limitation is the weight of this generator that sits on top of it. And even the current one is pretty big. It's like a small house on top of this pole. This is a person there. Okay. And the reason why it's very heavy is that the generator is made up of copper wires, and so they think that if they replace the copper wire with high temperature superconductors, then they can reduce the weight by a factor 2 or more. And the hope is that then they can make so I think currently the largest generators are order 3 or 5 megawatt per turbine, but now they think they can do 10 to 20 megawatt by using this technology. So it sounds very interesting. So maybe it will help solve our energy problem. Another application that I saw in Physics Today a few months ago is that they are talking seriously about building these transmission lines in Texas, because it turns out that the US has 3 major power grids that are not connected, and so they want to build it here so that they can interconnect the 3 power grids so that they can share power in case of power outage and so on and so forth. And so apparently it's technologically and economically really feasible to do this, and the decision is only up to political problems. Okay, so these things, I think, within our lifetime, may really turn out to be useful one day. Well, but we are physicists, so let me go into a little bit more about the basic features of these high temperature superconductors and how they work. So now, for us, it's very exciting because we have a new paradigm. We have something that's totally different from what we had before. So we got to understand it. At least we should try. Okay, so what is the basic feature of these blueprints? Turns out that the material is made up of layers of this material. The basic ingredients is a layer of this copper and oxygen system. So it's like a copper oxide. So remember I told you that many of these transition metal oxides are anti-ferromagnetic. And so this is actually an example of that. So the starting point is actually one of these non-insulated, where the electrons are immobile because of strong repulsion. So these high temperature superconductors is actually characterized by this very strong electron-electron repulsion, to the extent that they stop moving around and form this anti-ferromagnet. So this is what we call a non-insulated. So how did Bedfellows and Mueller did it? How did they manage to turn insulators into superconductors? Right? So that is explained by this headline, newspaper headline. I'll show you. They were doping, big time. You can look from the expression on their face. They're obviously guilty. Wow, okay. Doping is a technical term for physicists. Actually coming from the days of semiconductor transistors and so on. So what they did is they doped this non-insulator. And when they dope it, it becomes a superconductor. Okay, so what really happened which is lanthanum, which donate 3 electrons to the oxygen plane. So this is like an ionic crystal, right? So lanthanum likes to give up the electrons, it's very generous. So if you replace lanthanum by strontium, which is less generous, which likes to only donate 2 electrons, then there will be 1 electron deficit. So 1 electron will be missing, right? And so now, this is a process called doping. Doping is just either adding or removing electron from the system. That's what we do. Yeah. Oops. Yeah. And yeah. So somehow, when it happens, then you see these electrons are suddenly free, right? Because now there's a vacancy, and this vacancy. Now, when you have a vacancy, previously all these electrons are held in place; they have no place to go. Right? But once you remove one, then you leave behind what we call a vacancy. Then the other electrons can move. Right? So all of a sudden, the electrons are liberated. Okay. When that happens, and with quantum mechanics help, then this becomes a superconductor. So that, in short, that's what happens. So to show you this, I brought along my demo. So this is my high temperature superconductor. So I don't know, you're too young to know this toy, but I had one when I was young. So this is a vacancy, and when this vacancy moves around, right, then you scramble this image of the Batman. Right? So if you imagine instead of a Batman, you have an array of up and down spin, right? And once you introduce this vacancy by doping, then this vacancy running around is going to scramble up my anti-ferromagnetic structure, destroy my anti-ferromagnetic. And with the help of quantum mechanics, so if I have a quantum mechanical version of this would be a room temperature superconductor. It's very hard to find this. I think maybe you can find a virtual version of this on the computer. So I had a friend find one for me in Brazil. That's why it's French language. Because kids don't play with toys like this anymore. But very good try. So this is my high temperature. Yeah, so we can summarize and say, what is unconventional about high temperature superconductors? They are superconductor by doping one, by introducing these carriers and liberating these electrons which were otherwise imprisoned. Okay. So this strongly suggests that the origin of pairing comes from this, has to do with electronic repulsion, because now we're not talking about lattice, we're not talking about matrices, those are all happening. These are real, strong repulsion electrons. Okay, so they're totally different beasts from what I call conventional superconductors. And the proximity to this antiferromagnet indicates that the energy scale should be set by this antiferromagnetic scale. What causes the spins to be antiferromagnetic, rather than this lattice vibration scale, this matrix scale. Okay? And so that's a big revelation because it's free us from this very low temperature energy scale for superconductor, because this antiferromagnetic scale is not necessarily low temperature phenomenon. You see from the periodic table, the ferromagnet and antiferromagnet can live up to a very high temperature. Ferromagnet, the transition temperature is like 1500 Kelvin for iron, or even higher. So this liberates our way of thinking that superconductivity is actually not necessarily a low temperature phenomenon. So that gives us hope of achieving ever higher TC. Unfortunately, it took 25 years and nothing had happened. But never give up. But I think this is really a liberating idea. Okay, and in fact, in the remaining 20 years, it's not as if nothing had happened. Actually, we have made a lot of discovery. The field is collectively. We have many examples of unconventional superconductors of the same variety as I mentioned before. There is a whole class called organics. These are organic molecules that form, and they have a transition temperature of 12 Kelvin. Now, 12 Kelvin may sound very low, relatively low from the point of view of a superconductor, from everyday life. But remember, in those of you who know something about chemistry, in organic molecules, you're talking about electron moving between large molecules. So all the energy scales are factor 10 lower. So 12 Kelvin transition temperature is equivalent to 120 Kelvin transition temperature in the ordinary metal. So this actually, I maintain, is the second example of most high temperature superconductors. Another class we learned is something called heavy fermion superconductors. I don't want to go into that. But very recently I mentioned that there is iron-based superconductors with a transition temperature of 55 Kelvin. So it's not respectable. And in all these cases, these superconductors are in close proximity to an antiferromagnet. So this is a common theme. So what we are witnessing is a kind of marriage between superconductor and antiferromagnet. These two things that used to be mutually exclusive suddenly come together, and something marvelous has happened. So that reminded me of a quote by Roger Marx, that politics does not make strange bedfellows, marriage does, which was that's why the title of the talk. So finally, we want to ask the question, why does doping a bond insulator give rise to a superconductor? Right? So we know that that's what happens. You can see from my demo. But why? So a quantitative picture was given by Philip Anderson just 1 year, a few months after the discovery. And he called this a resonating bond idea. And that leads us to my last topic, which is unconventional antiferromagnet and spin liquid. Okay. So I think what we learned from this ideas is that an unconventional kind of antiferromagnet may be a partner to these unconventional superconductors. They may go hand in hand. Right? So it will be very interesting to study and understand these unconventional antiferromagnet. Okay. So now let me lead you through this last topic of unconventional superconductors. So I'll bring you back to the early days of antiferromagnet. Remember I told you that Néel, when he came up with this idea that electrons would form this up-down arrangement, was actually met with a lot of skepticism. And no less from the great theoretical physicist, Landau. For many of us, he's our great hero. He's one of the greatest minds in physics in the 20th century. And he was opposed to this idea. He didn't believe that this could work. Okay. For us, this is very strange because now, most physicists, most condensed matter physicists would think of antiferromagnet as a very commonplace, very obvious idea that the electrons will want to fall up and down. But it was not obvious in the 30s. And Landau did not believe it. But he's smart enough that he never wrote down his objection. I went through his collection. I heard stories that Landau did not believe in antiferromagnet. So I went through he has the two collected works. I went through it. And there's nothing that was said about this in his writing. So the only thing I found was that there was a obituary written by Jacques Friedel in 1991, which mentioned this conflict with Landau. And he says that, with this idea of antiferromagnetism, Landau suggests that quantum fluctuation can mix Néel's solution and give rise to reversal of moments. In modern language, what Landau is saying, if I interpret it for you, what he wrote, or what Friedel wrote, is that Néel's picture of antiferromagnet is a very classical picture. You have electrons that spin up and down, forming this static array. But quantum mechanically, the up and down electron can have a mutual spin flip, right? It can up down can exchange with down up, and that's a quantum mechanical process which is allowed in the system. And so Landau says that quantum fluctuation is going to flip. So if you start with this and you start doing this, pretty soon you're going to mess up the entire array, right? And so we say that quantum fluctuation can destroy antiferromagnetism. So Landau was a believer that quantum fluctuation can kill Néel's state. Now, it may sound very strange to us today, but remember in 1930, first of all, there's no experiment that demonstrated antiferromagnetism. This thing's never been seen. And secondly, there was a beautiful solution by Hans Bethe, an exact solution of a one-dimensional chain of this antiferromagnet. And the solution was that it doesn't hold it. In fact, quantum fluctuation destroyed it all. So I think that's probably what's behind Landau's objection. So Friedel went on to say that Néel's difficulty with antiferromagnetism, and in conclusive discussion in the Strasbourg as late as 1939, which is like 5 years after his made his proposal. People were still objecting. And he said that fosters skepticism about the usefulness of quantum mechanics. And this was one of the few limitations of his superior mind. So if you run into Landau, that can do permanent damage. So that's what happened to poor Neo. But, you know, he had the last laugh, because he turns out to be right. And in fact, for 60 years, almost every example we know, except for one dimension, you form this classical order state. So all the examples we know, Landau, Neo was right, and Landau was wrong. Okay, so, okay, well, except that in 1973, Anderson somehow, for some reason, started questioning this conclusion again. So, it looks like he might have independently started thinking along the lines of Landau. You know, great minds have a habit of having similar thoughts. So, he suggested that his idea of resonating state as an alternative to this what we call Néel state. So remember, Néel state is the state where, and he was thinking about a triangle lattice. You have a triangle lattice. In a triangle lattice, then Néel state actually has a kind of difficulty, because Néel wants to order the spin up, down, right? Up, down, up, down. But on a triangle, if this guy is up and this guy is down, this third guy doesn't know which way to go, right? Because if it's up, then he makes this one unhappy. If he's down, he makes this one unhappy. So there's no way he can win. So we introduced a technical term we call this frustration. So a triangle lattice is called a frustrated lattice. So he thought that on a triangle lattice is the best place to look for an exception to Néel state, right? Because that's when Néel's argument is the weakest. Okay? And instead, he suggests a very quantum mechanical state, which is a quantum superposition of this up, down, and down, up state. Remember I said that you can have a mutual spin flip between two states. So in quantum mechanics, you can take advantage of this by making a linear superposition, which we call singlet. So this is technically called spin singlet. And furthermore, instead of static singlet, he envisioned a linear superposition of all kinds of the singlet, which we call resonating wave as well. So it's a marvelous idea. Well, it's a marvelous idea, except that it didn't work for a triangle lattice. People pretty soon showed that, again, Néel was very clever, or nature was very clever. The way it escaped this frustration is by the spins compromising and pointing 120 degrees to each other. Right? So each spin can enjoy a little bit of the anti-foreign waves of its neighbor. Okay, so the nature managed to find a way to solve this frustration. And at the end of the day, it was Anderson who was frustrated. And so this field I dominated for a number of years, so nobody paid much attention to this, until high temperature came around. And Anderson suddenly remembered what he derived 15 years ago. And the idea is that with doping, doping comes again. If you can remove carrier, then these singlets will be liberated. So on PowerPoint, I can achieve doping very easily. So I just dope this thing by removing two of the electrons, and leaves behind these vacancies I was talking about. Right? And now you can imagine, just like in my demo there, that this vacancy now can run around. Right? And if the background is a superposition, a liquid-like superposition, then this thing can run around quite freely and become a coherent object. And now you can see that it's like a question of whether the glass is half full or half empty. Right? If you look from the point of view of the vacancies, there are very few of them, and they're just moving around, get kind of stuck. But if you look at the point of view from these pairs, they are exactly the Cooper pairs that we talked about, because this is a singlet pair of electrons. So you can think of this as linear superposition of super pairs, Cooper pairs that are coherent, and that's exactly a supernet. So this is a beautiful way of achieving a superconductivity by doping a quantum state. So that's the idea. So when these vacancies become phase coherent, we have superconductivity. So this is a beautiful idea, hard to either justify it or prove it to anyone who is moderately skeptical. And I think I'm convinced it's a true, correct theory, but it's very hard to make it a quantitative theory. And part of the problem is that in high-temperature superconductors, if there's some physics of this resonating wave responder we call spin liquid, they show up only at finite temperature. And it's very hard to make precise statement or experimental observation. So it would be very useful to have a spin liquid ground state, which we can study, we can hold in our hand. Right? If you can have one of these examples, what Anderson envisioned, before you dope, right, of this linear superposition of singlet that does not have the AL order, then we can study it and ask what it actually does, and then we can ask if we dope it, does it become a superconductor? So what is needed is an insulator, right, because we want these electrons to be immobile. One electron per unit cell, we want one electron per site, and it should not order. It should not order in the AL state. It turns out that this is extremely hard to find. And after 30 years, it was only in the last few years that physicists finally have 2 or 3 examples that are quite convincing, that we think is very promising, that we finally have discovered this spin liquid state. So for me, that's a time of great excitement, because this ends a drought of spin liquid. You see, even though we only have 3 drops of spin liquid, for someone who's been dying of thirst, this is a godsend. So we're very happy, some of us are very, very happy with this development. So I want to share with you some of the excitement. Okay. So one of the examples is so-called Kagome lattice. So remember, Anderson was frustrated because he has a triangle lattice. So it turns out that if you remove some of the sites from the triangle lattice, you form what is called a Kagome lattice. And this is the most frustrated of the 2-dimensional lattice. And this one, people believe, really can support a spin liquid state, if you can make it. The name Kagome is a Japanese word which describes the basket with this kind of pattern. Okay. And so this is my demonstration of the spin liquid. I was flying to Japan to attend a conference on frustrated magnet, and this thing showed up on my dinner tray. So I thought that was a good omen, so I kept it. So it has this beautiful pattern of this triangles, corner sharing triangle, in miniature form. That one is bigger. So that's all the demo I brought. Yeah. So theoretically, I think people have quite a good understanding of this Kagome lattice. But the trouble is that, why would nature grow a thing like that? This is kind of oddball crystal, right? It's hard to imagine that such a thing would actually even form. So, turns out that one of the few known examples, that there are actually very few examples of that this kind of structure actually exists. And 2 of my colleagues, Daniel Serra, who's a chemist, and Yang Li, who was a physicist, collaborated to make these materials and study them with neutron scattering. So this is an example of materials preparation working hand in hand with experimentalists and with some theories poking around in the background. Yeah. So in the early example, they can only make spin 5 half. So this is a very classical spin. It doesn't quite satisfy what we need. But this is a class of material called jarosite, iron jarosite. And they were working on it for a number of years, about 6 or 7 years ago. So some of you may remember that in 2004, we sent a rover to Mars, right? And then you read in the newspaper, in the news all over the place, that we have discovered evidence for water on Mars. Right? You remember that? Do you know what the evidence is? What's the evidence? Well, okay, so this is from the NASA website. So they send this rover roaming around. They find a piece of rock that they like. So then they drill into it, right? And analyze what's there. They have a machine called a MOSFET. They take a MOSFET spectrum. And they discover that the first mineral they drill into is an iron jarosite. Now, why does this prove, and this is a proof of water. Why is this the case? Well, this mineral is a very rare mineral on Earth. They're called jarosite because they were discovered in Spain, in a remote region in Spain called Jaros, in 1852. And they grow, they form, because of the chemical formula. See, there's an OH there, right? It's zinc, copper, and OH, and chlorine. They form in a sulfuric. They need dilute sulfuric acid in groundwater to form. Okay? So, because the first mineral they found on Mars is the iron jarosite, that must mean that it's very commonplace, and that must mean that there must be water on Mars at one point. So that's the reason for saying that there's evidence for water on Mars. So when I saw that, I almost fell on my chair because I suddenly realized that all this time I've been living on the wrong planet. The Mars is covered by this stuff. So the history of magnetism would be very different if we were written by Martians. Nail would never have gotten his Nobel Prize. So they worked much harder, and 3 years ago, they managed to finally find the spin-and-a-half cargo weight system. And indeed, this system has no ordering down to millicount, even though naively you would have expected that if they were right, they would have ordered at 1 or 200 Kelvin. So 5 orders of magnitude below where she ordered, there's no sign of ordering. And by the way, this is also a natural mineral that was discovered in Chile. It's amazing that as late as 1972 you can still discover minerals. And it's called Herbert-Smithite in honor of Herbert Smith, who was a British hydrologist from the turn of the century. He didn't discover it, it was named in his honor. So what Sarah did, it's one thing to find a mineral, which usually has lots of defects and so on, but you have to find ways of making a crystal, a high quality crystal, to study it, and that's what the achievement of that Sarah. So many of us are very excited by the discovery of the new state of matter, because this is really the spin liquid, long promised, long sought after spin liquid that does not order, and very likely is describable by this resonating valence bond idea. So we finally have on our hands something that we can study in this ground state, and we would be looking for more emergent properties. It doesn't, so far it's characterized by what it's not, what it doesn't do. But theorists believe that there are very interesting things that it will do. And that's the subject of our discussions in the last several weeks. So I'll summarize here. So I think my main theme is that the hatred of electrons for each other is very deep hatred. And quantum mechanics are the key ingredients which are responsible for very commonplace phenomena, such as magnetism, and more exotic phenomena, such as high temperature superconductors. And these strange bedfellows have opened up a new realm of possibilities for us, so we can imagine and dream about much more exciting things. And let's see what more surprises nature has in store for us. Thank you.
We have some questions for Professor Liu.
So can they go Herbert-Smithite?
They're trying. Yeah, but I'm not optimistic. Yeah, so actually we did a theoretical study of this and predicted there should be a superconductor with rather exotic properties, but
how strong is the exchange coupling in that material?
it's about 200 Kelvin, so it's substantial. Yeah, the high temperature superconductor is actually quite unique. It's one of the few materials that you can dope without and still become metallic. And the reason is that the exchange, this anti-ferromantic energy, is extremely large. It's the largest that we know actually in the transition metal oxide. And so So that's the reason why that particular system and no other is a superconductor hydrogen.
Do you imagine there will be a theory for high TC that's as conclusive as BCS theory for low TC materials?
Yeah, that's a tall order to fill because BCS theory is, I think, the most successful, probably the most successful physical theory because they left out somehow. There's a very simple mean field, what we call mean field theory, and it works for various reasons. To have something as simple as that, describing phenomena as complicated as I think it's not hopeful. But I think we should have an understanding. Well, in my opinion, we already do have a very good qualitative understanding of the physics. And I think what we need is more experiments and more examples. If we can create more examples, so far we have one material to study. If we can create more examples of doping of one insulator, even at their lower transition temperature, I think that would be very interesting. So that's why one reason I'm very interested in this organic material is I think that's actually another example of the same phenomenon. So I think we need not just theory, but more data and more examples. Now, with a system as complicated as this, it's hard to do pure theory. So we really need this triangle to resonate: materials, experiment, and theory to gain an understanding.
Do you think there's much hope of increasing above 150 Kelvin?
I don't know. It can happen tomorrow. Who knows? Yeah. This whole field is built on serendipity, right? So that's the theory is not developed. I mean, that's the answer to the question, right? The theory is not sufficiently developed to be able to predict. You take this material and make a superconductor. Even for conventional superconductors, the original BCS theory was not able to do that. It took many years of development. Now people can start to predict transition temperature with reasonable accuracy, but it took 50 years to make it a predictive theory. And so, yeah, I mean, in principle, if you can find a system where they exchange, just like the Coupé with an energy scale which is a factor 2 higher, we would get room temperature superconductor. But as I said, this is already maybe somehow nature has already optimized this particular one because it already has the biggest anti-ferromagnetic interaction in the region. But maybe there are other ideas. The doping of one instead of maybe just one route.
Besides developing the compound, do you think there's any intrinsic upper limit to how high TC can go?
Besides
Developing something. Besides seeing what the material will melt, is there any intrinsic, do you think there's any intrinsic upper limit to how high TC can go?
Oh, intrinsic limit. Well, in neutron stars, we have superconductors with TC of I don't know, billions of degrees, right? So there's no intrinsic limit. On Earth. I'm a Martian, I prefer to live on Mars. I don't care what happens on Earth anymore.
I can understand how temperature will have an effect on superconductivity, but how the hell does pressure have anything to do with it?
Oh, pressure changes the chemical environment of the material.
So it just changes.
So, for example, it can increase with increasing pressure. It can increase the energy scale for these anti-ferromagnetism.
So you're just changing the
Fundamental parameters. Yeah, you could. That's one possibility. We don't fully understand why pressure increases the transition temperature so much, actually. Yeah. So yeah, the theory is not well developed in that sense.
So were Lee and Nocera originally aware of the structures of jarosite and perismethite, or did they kind of
Stumble upon it. They probably knew. I didn't ask them, but Nocera probably knew that these naturally existing minerals. And the trick is to make them into crystals. But now they are beautiful crystals this size. So I think they can now do very nice experiments. But it takes a long time. Growing crystals is very time consuming. And our community don't reward these people very well. So that's part of the problem.
Is there something someone Anderson didn't talk about, by the way?
Hmm?
Did he know about it?
I don't know. No, he's not God.
I know.
He's a closest approximation, but you can't expect him to know everything.
It's a well-known lattice for the Ising model, so he was certainly been aware of it because it was a known solution to the Ising model.
Yeah. But I think people just kind of gave up after. They were not, the field kind of died and would have remained dead like, if it were not for Heisenberg's.
Okay.